Now that we have the basics of quantum entanglement under our belt, we're ready to tackle Schrodinger's cat. But not literally, because that would be animal cruelty. Also, that cat must be dead by now. It's been a long time, so it would also just be weird. Today, the Schrodinger's cat thought experiment is often used to explain or illustrate the weirdness of quantum mechanics to people. But when Erwin Schrödinger first came up with this thought experiment, he did so to illustrate what he viewed as the absurdity of the prevailing views or the prevailing interpretation of quantum mechanics. In particular, his argument was that the combination of superposition and quantum entanglement led to absurd results. So first, let's start with the basic setup of this experiment, or rather the hypothetical setup, because first of all, carrying it out for real would be animal cruelty, and also it's not really practical or possible to do in a controlled enough way for the experiment to actually function. But we can imagine it working, and we can imagine the setup, and as long as we consistently apply the rules of physics, we can conclude what would happen were we actually able to do this. We start out with just a box, and in principle, this box actually needs to be a little bit special. It needs to perfectly or nearly perfectly isolate its contents from the outside world and vice versa. That means no transmission of sound, no transmission of vibrations, no transmission of any kind of light or anything like that. In reality, it wouldn't be possible to build such a thing perfectly, but we could also actually make do with almost perfect. The next step is to put a cat inside the box. Next, we place a canister of poison gas inside of the box, and we hook up this canister to a sensor containing a single radioactive element inside of it, and this sensor is programmed to open the canister of poison gas when the radioactive atom decays. And finally, you come along and you close the box, isolating whatever's going on inside the box from whatever's going on outside the box, including yourself. In order to move forwards any farther, we need to take a step back and we need to talk about this radioactive atom. As you learned in chemistry, radioactive decay is a random process. For example, we often talk about it in terms of half-life. If something has a half-life of 1 minute, it means if I start out with 1 million of them, after 1 minute, I would expect half of them to have decayed. And if I wait another 1 minute, I would expect half of the remainder to decay. But because this is a probabilistic process, if I don't have a large number of particles to begin with, the half-life is not going to be a very accurate way of determining things, because if I have a small number of particles, there's a reasonable chance that maybe a little bit more or maybe a little bit less than half of the particles will decay within the next half-life. This is especially apparent when there's just one particle left. If I have a single particle left and I wait one half-life, half of my particle can't have decayed and the other half not. The last one either decayed or it didn't. So instead of half-life, we can also talk about simply the probability of a particle to decay within some given time period. There's actually a simple mathematical relationship between these two. We can always calculate the half-life of something as the natural log of 2 divided by the probability per second of an individual particle to decay. For example, if a particular type of particle has a 50% chance to decay per second, then the half-life of a large collection of these particles would be about 1.4 seconds. If you put a radioactive particle in front of you and you wait, as time goes on, the probability that the particle will have decayed goes up. But if nothing is measuring this state, then what's to determine whether or not the particle decayed? And in fact, just like an electron can be in a superposition of being in the spin up state and the spin down state, which are clearly not the same as each other, and in fact they're kind of opposites of each other, particles, radioactive particles, can also exist in superpositions of having decayed and having not decayed. You might say that makes no sense, but really it's the same idea as spin. Of course, classically it doesn't make any sense at all, but we are not talking about a classical world. We can illustrate this by writing down the state vector for this particular particle. At any moment in time, it has a probability of being found in its initial state, but it also has some probability of being found in its decayed state. At t equals 0, when we first begin counting, a has to be equal to 1, because the probability of finding the particle in its initial state at the moment we put it there has to be 1. Likewise, therefore, B has to be 0. It hasn't decayed yet before we've given it time to decay. As time approaches infinity, these switch. If we allow an infinite amount of time to go by, the probability that the particle decays will have approached 1, and so B will be 1 at t equals infinity, and A will have gone to 0. This leads to some pretty strange effects. For example, if we wait a pretty long time before looking at our particle, chances are we'll have found that it has decayed, because B will be almost 1 and A will be almost 0, so when we look at it, the state will collapse, the superposition will collapse, and most likely end up with a decayed particle. Some small chance that maybe it hasn't decayed yet. But what's interesting is that if I look at the particle after a very small amount of time, A will be nearly 1, B will be nearly 0, and the amplitudes are squared to find the probabilities. And I will almost certainly find that the particle is in its initial state. But the moment that I measure this particle, the wave function collapses, the superposition collapses. And the moment I measure that my particle has not decayed, I start over. A is now 1 because my state is this, and it's not this, so B is 0. And if I perform a measurement a very short time after that first measurement, once again, I'm almost guaranteed to find that my particle is still in its initial state and that it hasn't decayed yet. And once again, I reset the counter. And if you actually do the math, you can show that if you perform periodic measurements in really short time intervals, you can actually delay or prevent the particle from ever decaying. Because again, each time you look at it after a short enough amount of time, A is almost exactly equal to 1, which means you're almost guaranteed to find that it hasn't decayed yet, and then you reset A back to exactly 1, and you restart that process. And if you take the limit, if you were able to perform continuous measurements of your system, the particle would actually literally never decay. It would be stuck. This is actually true for any unstable quantum mechanical state. If you look at or measure an unstable state frequently enough, you can essentially prevent it from ever decaying. It's camera shy, if you will. A watched particle will never decay. This effect has a name. We call it the quantum Zeno effect, as a reference to Zeno's paradox, which is kind of similar in some regards to this. I brought this up for 2 reasons. One is it's cool, and cool things are fun. We don't need a reason for that. The second is that the quantum Zeno effect has been measured. It's been experimentally verified. This is in fact true. If you perform repeated rapid experiments on an unstable system, you will delay or prevent its decay. And this is wildly inconsistent with classical physics. Classical physics cannot reproduce this particular prediction, which again has been experimentally verified. And so that is very strong evidence that these decay processes are in fact best described in the language of quantum mechanics using superposition. So it's our best understanding that if you have an unstable isolated particle and you wait a while, that particle can be described as in a superposition of its initial state and its decayed state. And it's not collapsed until a measurement is performed on that system. So now let's go back to our Schrodinger's cat thought experiment, and let's take a look at what's going on here. First of all, I'm going to make the box see-through, but again, just so we can talk about this, remember this box is perfectly isolating whatever is inside from the outside environment, so that you standing here next to the box, you have no idea what's going on inside. The moment you close the lid at t equals 0, the radioactive particle is still in its undecayed state because you literally just put it there, which means the poison gas is safely contained inside of its canister, and therefore the cat is alive and well. But as time goes on, the radioactive particle enters a superposition of not decayed and decayed. And if it hasn't decayed, then the gas is safely contained. And if it's contained, the cat is alive. But if it has decayed, the gas has been released. And if the gas has been released, the cat is dead. According to the logic of this experiment, if the radioactive particle is in a superposition of not decayed and decayed, then the gas is in a superposition of contained and released, and therefore the elephant is in a superposition of alive and dead. Another way of putting this is that the state of the cat is entangled with the state of the radioactive particle. And as long as we are treating the inside of this box as a quantum mechanical system, then from your outside perspective, this system remains in a superposition until you open the box and measure it. So from your outside perspective, the box is in a superposition of having a safe but possibly annoyed cat and being filled with a deadly gas and a dead cat. This all might seem a little bit absurd to you, and as well it should. From a certain perspective, at least, it doesn't make any sense. Who cares if you haven't opened the box? Presumably the cat knows whether it's alive or dead. The cat is a living creature. It doesn't need you to tell it that it's alive or dead. It knows. And again, one of the reasons why Schrodinger came up with this little thought experiment was to indicate the absurdity of taking the logic of quantum superposition and entanglement and extrapolating it up to macroscopic systems. And so here we see that by placing this importance on our measurement of this system inside the box, we've created a little bit of a silly scenario. Now, if we had the particle over here in a superposition of state, and it was able to interact with some other quantum mechanical particle, and there was a third quantum mechanical particle in here, then this doesn't seem so crazy anymore. It isn't unreasonable to think that the superposition of this particular state could be entangled with this other quantum mechanical system, maybe another particle, which could be entangled with a third particle. So if we think of the radioactive particle, the gas canister, as well as the elephant, instead as actual quantum mechanical things, maybe individual electrons or something, then all of this logic checks out. Then it's reasonable to say that the system inside this box remains in a state of superposition until some measurement is performed on it. But since the system that we actually described involves a cat and a canister of gas and all, presumably something is being measured in here already. And so what this really does is it really raises the question, what is a measurement? What constitutes a measurement, and what causes wave functions to collapse? Does an electron bumping into another electron cause their wave functions to collapse? Can this detector collapse the superposition of the particle so that the particle is in a state of superposition but collapsed by this so that the gas canister is either released or not? It sounds reasonable, but at the same time, the particle detector is made up of quantum mechanical things. It itself is just composed of atoms, which are composed of electrons and protons and stuff, and those are all quantum mechanical particles. So where does the buck stop? Because again, we know that if we put a cat in this box, the cat is not simultaneously alive and dead. The cat is either alive or it's dead because the cat knows the answer, even if you don't. Just like Alice and Bob's marbles were red or blue, one or the other, definitely, it wasn't really up in the air. This is just the correspondence principle in action. We know that at macroscopic scales, this phenomenon of quantum superposition and the resulting strangeness of quantum entanglement don't exist. They get washed out somehow. But where is that point? It's actually a really hard question. This is called the measurement problem. And it's not resolved. I don't know the answer, and neither does anybody else in the world. There are a lot of ideas, and each of these ideas come with their own way of interpreting what is really happening in quantum mechanics. And this is why the Schrodinger cat experiment persists so predominantly today. First of all, it's a really simple setup. It's really easy to talk about. And it also serves as a very useful testing bed for what different interpretations of quantum mechanics mean. Is the cat in a superposition of being alive and dead? Or is the superposition of this particle not really effective until the wave function collapses and it actually decays, causing the gas to flow out? Or is it something else entirely? So what we're going to do, we're going to talk about these different interpretations of quantum mechanics, and we're often going to come back to what do those individual interpretations mean for the Schrodinger's cat experiment. We can actually take this thought experiment farther. A physicist named Eugene Wigner extended it so that rather than just having a person with a unfortunate cat trapped inside of this death box, imagine this is all taking place inside of a lab. Usually we treat this lab as Wigner's lab. So he has this lab, he's got this box with a cat in it, and he brings a friend. Wigner and his friend close the cat in the box, and then Wigner steps out of his lab and closes the door. Wigner is now external to the system of the lab. So he doesn't know whether or not his friend has opened the box or not. And so the way he sees it, there are three possible states of the lab and all of its contents. Or in other words, according to Wigner, the lab is in a superposition of three states. One possibility is that his friend has not yet opened the box and is anxious. Another possibility is that his friend has opened the box and has found the cat alive and well, and so his friend is happy. And the third probability is that Wigner's friend has opened the box, found a dead cat, and is very sad. This just emphasizes the problems raised by the original experiment, right? In the original experiment, the problem was that even if you don't know whether the cat is alive or dead inside of the box, presumably the cat is well aware. Here, it's even more on the nose because as far as Wigner is concerned, it's not just the cat experiencing a state of superposition now, but his friend too, a person. According to Wigner, the state of the lab, as long as he hasn't, opened the door and checked, is in a state of superposition of an anxious friend and the superposition of the cat being alive and dead inside the closed box. So a little bit of nested superpositions going on here. As well as a happy friend and live cat, and a sad friend and dead cat. And clearly, if you are Wigner's friend, it doesn't make sense for you to be of three minds. It doesn't make sense for you to simultaneously be wondering about what's going inside the box and being anxious, being happy that the cat is alive, and at the same time being sad that it's dead. If that does feel like an accurate description of your life, you should talk to somebody. I want to emphasize again that these thought experiments' usefulness is not in their ability to answer questions, because it doesn't do that, but rather in their ability to raise them. Does wave function collapse occur? Under what circumstances does it occur? And to what extent does it occur? The amazing thing is that those questions are foundational to what quantum mechanics means for what is actually happening in the world around us, and yet we have no idea what the answers to those questions are. The standard interpretation of quantum mechanics, the one that I've been teaching you, called the Copenhagen Interpretation, or in some cases like a slight modification of it, is built on the idea of wave function collapse. But there are other interpretations of quantum mechanics in which wave function collapse isn't a feature. And in fact, there are some good reasons to believe that wave function collapse might not actually be a good way of describing the world. We already saw that it violates locality, but we also showed that that's not really a problem, at least not with special relativity. But it also breaks something that worries physicists a lot more, which is called unitarity. The problem with wave function collapse is that we can't describe it with equations, or rather, we don't know how to describe it with equations. We can describe how a system interacts on its own, and we can predict what will happen after a measurement, but we actually have no mathematical way of modeling how the state physically collapses. It's just something that's kind of done by hand. And that's uncomfortable because in the end, even if I go and measure something, I am made up of quantum mechanical particles, and the thing I'm measuring is made up out of quantum mechanical things. And so the equations that govern quantum mechanics being unable to describe the process of wave function collapse seems like a major inconsistency. I'm going to leave you with 4 different terms that are important in any discussion of how to interpret the mathematical model that we call quantum mechanics. The first is the measurement problem, which I've discussed in this video. The second is the principle of locality, which I discussed in the previous video. The third is one of my favorite terms in the entirety of the English language, which is counterfactual definiteness. And the last is something called local realism. I'm not going to define the last 2 of these for you right now. That's going to be your job with a little bit of research. It shouldn't take very long. Next time, I'll introduce Bell's theorem and how it lets us carry out experiments that allow us to rule out the interpretations of quantum mechanics that most people instinctually want to believe, including, for example, Albert Einstein.